Hello again, fellow YouTubers. Today we are going to have a look at this chipKIT Uno32, which is a Arduino form factor board, but it contains a PIC32, and this one is made by Digilent, but uses the microchip PIC32. So let's open up this and have a look at the peripherals and the features of this small but very expandable and feature-filled board. Inside the board, as usual, very good packaging. Well, I must admit that the packaging has become better in the last couple of years from all development board manufacturers. Those some are better than others, but this board is not in the expensive end, so this is good packaging at a reasonable cost. Inside we find the board itself. Here, the Uno32 board, which you'll see looks much like an Arduino. Compared to an Arduino Dumalano I've got here, you'll notice that it's exactly the same form factor. Oh, I should turn it around. We got the same pins, as you can see. We got here we got the rows, the large rows and the small rows. Here is the analog, which is over here. But one thing you will notice is that the Uno32 board actually got some extra rows in here, 4 extra IOs. So this board has got extra IOs. But let's start to look at the chip itself. This one. This is the PIC32 MX320F128. This chip has got 128 kilobytes of flash, compared to the 16 or 32 kilobytes of flash on the Arduino. And as the name says, Uno32, this is a PIC32 chip, which means it's a 32-bit chip microprocessor running at 80 megahertz. The great thing is also the large amount of RAM. This has got 16 kilobytes. And compared with the Arduino, the programming is actually the same. This board does also contain a small FTDI chip for converting the USB into a serial port, which simply connects to the serial port pins we see here. It's the same thing as on the usual Arduino boards. Or, well, the latest Arduino Uno uses another USB chip instead of the FTDI ones. Okay, so the form factor is the same except for the extra IOs. And these extra IOs gives a total of 42 IO pins that can be used. And 12 of these are also analog inputs, which we got in this connector. The board itself is actually 3.3 volts, and it can be this voltage can be derived either by the USB port or by an external jack where you can input up to 15 volts. Then you might think of a problem because of this board being 3.3 volt and compared to your 5 volt shields or 5 volt circuits. But the great thing is that all of the IOs are actually 5 volt compliant. Inside the PIC32 chip, they are 5 volt compliant except for the analog inputs. But Digilent decided to make these analog inputs 5 volt compliant too by adding a series resistor and pull-up diode, a so-called clamping diode. So the board itself is 5 volt compliant and is also compatible with previous shields, or it should be, and you might have to make some changes to the libraries to get it working properly. The peripherals itself of this chip is mostly the same of the Arduino, though it got some extra features. For example, as I said, it got 42 IOs and 12 analog inputs, but then it got 2 UART ports. Instead of the only one here, it got 2 hardware UARTs, which can be used separately or individually, and you don't have to make a software UART as you would have to on the Arduino Dumalano or Uno. Then it got I2C and SPI, where it actually got a header here for selecting which mode you would like to use, the SPI mode, either master or slave mode. And you also got some toggles here, where you can select, on some of the pins, you can select which of the microprocessor pins you would like to use to route out to the connector, because the pin can have, the microprocessor pin can have different functionality. Another thing is 5 PWM outputs on the digital pins. So 5 of those are in PWM, and 5 of those are also interrupt. So you can use them and trigger something in the code, either a timer interrupt or a software interrupt. Compared to the Arduino, which only the Arduino Dumalano or Uno, this one has only got 2 interrupt pins, the Atmega 168 or 328. Then it has 5 built-in timers, so you can set them up at individual different frequencies to run, either interrupt based or for PWM. Those timers will also be used when you in the code decide to use some PWM or decide to just run a normal Arduino sketch, which probably uses delay. This uses one of the timers. Then compared to timers, it has also got a real-time clock. This though requires connection of an external oscillator or crystal, and then you will be able to plug this into a small battery, and then let it run. Set the real-time clock and let it run when not used, and then you can read the time when you would like to. Last but not least, it has also got 2 onboard LEDs, as we see over here. Yep. I think that's the ones. Yeah, those LEDs over here are the programming LEDs for the FTDI chip, while those 2 over here are the onboard LEDs that connects to a pin on the microprocessor. And to view on that, Digilent have made a very good chart. There's a link on our blog too, but this chart actually describes the connection diagram compared to the, up here we can see, compared to the Arduino, the Atmegas, and then the Uno32. It shows which pins are used for what, and down here we can see how it is used, the Uno and the Mega, and then the chipKIT, which of the pins they are using. This chart is especially good if you would like to port some already existing libraries to the chipKIT, as you would need to look up the shield connections. And this chart of course shows the original pins on the other Arduinos, but then it's also showing the new pins, like the extra UART. You can find the serial TX, we got one here, and we got one here for both of the TX and RX, and then we got one that's not listed in here, but we got another one on the board. So this chart is very handy for library porting. Alright, so I think we should have a look on the new IDE, because the board itself doesn't integrate with the the normal usual Arduino IDE, because it's another compiler that is necessary to compile code to this PIC32, and the bootloader is also different. So we will have a look at the compiler, and I'll make some comparison to the other ITET Mabel I've been talking about before, which contains the STM32 Cortex M3 processor, and make a comparison on speed performance. And then I'll at final I'll have a try with this board and the touchscreen display I've also got running on the Arduino and on the ITET Mabel. Okay, here at the computer I've now visited the Digilent homepage just to show you the two different versions of the chipKIT they got. Here is the chipKIT Uno32, which I'm currently showing to you. You'll also notice the price. That's not very much compared to this board being a 32-bit 80 MHz board. And you'll here also be able to read some of the features I've told you about. But what is really interesting is this chipKIT Max 32 board. It's the larger version, the big brother, and it's very comparable to the Arduino Mega. You can see that the form factor is the same, though once again they've also added some extra pins because of the bigger chip. The other thing to notice about this board is it's actually got a built-in Ethernet PHY and a USB on the go connector. Oh well, it hasn't got the connector, I mean the peripheral. So you'll be able to buy a network shield. It's also on the Digilent homepage, and this networking shield connects on top and enables you to connect a Ethernet cable or a USB client or USB host cable or device to the board itself. This is a feature that the Uno32 is missing, which is a pity. But anyways, even that this got the USB device peripheral, it is still using the FTDI connector, the converter chip, compared to the ITET Mabel, or the Mabel, which is using the built-in or their own bootloader, which is programmed into the flash, and it is a USB bootloader for programming the device itself. But anyways, as I said, we are going to use another compiler, and I've downloaded here. So I'll first let you know that if you're going to install new libraries, I've had some issues with this because I haven't had any luck with just putting them into this libraries directory. It seems like when I put them into this, it isn't actually detected. So instead I had to go into hardware, into PIC32, and then into libraries and put them into here. So let's open up the compiler and see what it looks like. As you'll notice, it is very similar to the normal Arduino IDE, and we will be able to open up an example sketch here from the standard Arduino examples, and then here from the library examples. But let's simply just open up this blink, and then we can see that we got a simple blink, and up in the tools we'll be able to select the board, and you'll notice that this is actually a expanded list of boards. It's not only the chipKIT boards, but it's also other microchips and also the Arduinos. Excuse me. I don't know why this always happens to me when I'm reviewing. But anyways, you can simply select which board you would like to program to. Also notice the microelectronica boards is actually supported. But let's hook up the chipKIT board and program this blink sketch into the board. So now I'm going to hook up the board. As you'll see, we plug in the cable to the computer, and it is detected, and this power on LED turned on, and we have a status indicator here over here. Now it is ready to go. So we will be able to program this blink sketch by pressing the upload button. And it will upload, as you'll see, notice here. And now it is programmed, and you'll notice this is the pin 13, where the normal status LED is also placed on the Arduino. And you'll notice that this simply blinks, toggles once a second as programmed. So that's a very simple and basic blink sketch, but just to show that this board is working and is very easy to get started with, just as easy as the normal Arduino, as you can program in the same language and in a similar IDE. Right. We could also load up some other example sketches, but I would like to talk about some shield compatibility, because one of the problems with the board is, as I said, that this board is running at 3.3 volts, so you would have to make sure that your shields will be able to handle those 3.3 volt signals. The board itself is capable of handling 5 volt shields, so meaning that it can handle 5 volt inputs, but if your shield doesn't support the 3.3 volt outputs seen as high, then you got a problem and the shield will be incompatible with this board. But actually the Ethernet shield, this is one of the old ones, original from Arduino, are actually supported by the board. These one will be able to run at 3.3 volt, but the problem is that they've changed these boards and made new revisions and added the use of the programming port, this in-circuit serial programmer port located here. So on the newer revisions, a header has been placed here which plugs onto this connector, where the SPI pins are also located. That is made to make the Ethernet shield more versatile, which means that it could be used with both the Arduino smaller Arduino Dumaleno or Uno, but it could also be used with the Arduino Mega, where the SPI pins are actually located on another set. On the usual connectors, but are located the same place on the ISCP connector. ICSP, sorry. But this board I've got here hasn't got that one, so I'll only be able to use this for the Arduino Dumaleno or Uno without making any changes, modifications. But the great thing about that is that I'm able to simply plug it into this, because the new Ethernet shields can't actually be used directly with this board without any modifications, because Digilent has made a small mistake on this ICSP connector, where they placed both an SPI master and an SPI slave chip select instead of the usual chip select, and where they placed one of the chip select is actually where the reset pins to this board goes. And the problem is that the reset pin on this shield from the connector on the back, where the reset pin is connected on the shield to the same reset pin over here, which we got there. This means that when this board toggles the other chip select, which should be the reset pin, it actually resets the board itself. So you would have to cut the trace on the board from the reset pin over here to the reset pin on the bottom connector to get it working. But in my case, I haven't got that connector, so I haven't got that problem, and I can simply plug it into the board and get it working. So let's hook up an Ethernet cable to the board. We've got one here, and let's see what happens. Back on the Arduino, the MP IDE, we can open up an example sketch from the Ethernet library, and let's choose the web client example. And in here I'll simply change this to match. Well, I'll select web server instead, just to show you that it works as a server, and then we can take client afterwards. Web server. I'll plug in, put this in, so it will be okay, and I'll press the upload button, and we'll give it a go. And as you'll notice on the board, it will start blinking on the Ethernet shield with the LEDs when it has been programmed, as it has been now. And now when I enter the IP address in our browser, you will notice that the LEDs blink on the board, and on the browser we get these analog input readings. And as we haven't connected anything on the analog inputs, we can't use these readings for good. I can refresh and these readings will be totally random. Yeah, well, somewhat random. Okay, but as you can see, when I refresh, it blinks the LEDs. So the Ethernet shield in my case works as expected, and I'll also be able to load up the web client example, and I'll show you the serial connection by the FTDI chip, and see how that works, because this web client example connects to Google, and makes a search query for Arduino and then returns that to the serial port. So we'll open the serial monitor up here, and we will notice it's saying connected in a minute, connecting. And then we'll wait for it to connect to the Google server, if that's correct. I actually can't remember. Well, that might be wrong. Let's check that. Oh well. Traceroute google.com, and let's see what that says, because over here it said connection failed. So the IP might be wrong, but anyways, this will be working. There's also some other examples, for example Ethernet UDP send and receive string, which simply connects to, or makes a UDP server client thing that you can send strings to, and it will return acknowledged and write the string to the terminal port. Well, Google seems to be down, or is it just me? Well, I think it's my internet connection. Right. Okay, anyways, the Ethernet shield works as expected, so let's continue our walk through the board with a comparison with the ITEP Maple board. Before making the comparison to the ITEP Maple, I'll just show you what I've got working with this touch shield from ITEP Studio. This is a 2.4-inch touch shield with a QVGA display, which plugs directly into a Arduino Duino or Arduino Uno, or this can also be used for Arduino Megas, but they also got a bigger sized version that also speeds up the connection. But as this connects directly on top of a normal Arduino, I decided to have a go with this chipKIT and see if I could port the library from the Arduino to the chipKIT, which I've also done with the ITEP Maple. So by plugging this into the chipKIT, you'll see that it lights up. And now let's program the library I've made. Let's load up one of the example sketches from this, the demo landscape, which is a usual example which shows the Henning Carlsen library, which is the one who made this QVGA library in the beginning. So let's load up that and see how it performs, because it performs much better compared to a normal Arduino, where the speed is reduced due to the lower frequency. And we will afterwards load up the same sketch on the Arduino to compare, so you will be able to see the speed difference. But here now it's loaded up, and you'll notice the display starts to display different things, and you'll please notice the refresh rate here, especially with these lines and with the random circles and colors for squares, etc. And now it's finished, and it says down here at the bottom 26,951 runtime in milliseconds. That's how long it took to go through the different pages, and then it starts all over. So let's try to find our Arduino and program this with the same sketch. I'll get a USB cable and plug that into the Arduino. There. And then I load up the Arduino IDE and do the same programming of the same example. Just have to find the Arduino IDE, sorry. Open that. And here we will notice also the similarity in the compiler. They are both building on the processing language. So in the examples, I'll open up the same here from ITDB02 graph. I'll pick the demo landscape and program, upload that to the board. Oh well, I think I have to select the serial port. Oh, that might be right. Okay, so that will be programmed. I will plug this out and put the shield on top of this other Arduino, and you'll notice the speed difference in a minute when it has been programmed. And uploading's done, and you'll notice the same graph shows up, but please here you can see here indeed that the speed is has changed. It's much slower in refresh rate, especially here at the circles, but also later on with these lines, much slower. And this is partly due to, or mostly due to the lower frequency, but also due to the 32-bit calculations and the lesser operations for moving data out on the ports than the Arduino itself. You see it takes a lot longer. Here it says it's finished in 44,200. So that's over 10 seconds more than on the chipKIT. So you'll be able to do much faster graphics on the display when using the chipKIT than a normal Arduino. And of course I've also converted the other examples. For example, let's load up the bitmap example, which shows the capability of displaying graphic bitmaps. So now we're waiting for it to be programmed. Notice the programming LEDs up here. And now it is programmed. You'll notice here we have some bitmaps and some larger ones. This is actually the raw bitmap, and then it has some software capability of scaling it up. And this is again Henning's library with this graphics routines. So this library is fully working for the display, except for the touchscreen. The touchscreen and the SD card here hasn't been ported yet, but the graphics support of the QVGA QTFT display is fully working. So now let's have a go and make a comparison with this iTet Maple. This is, as I said in my other video, on the link here below. You can click here and view the review of this board, this is very similar to the normal Maple board, which is also an Arduino form factor board, but with an ARM 32-bit processor. This one is the STM32, and as you'll notice, it's the same form factor. Let me just unplug this. You'll notice that it's the same form factor. We got it here. But one of the main differences on the boards is that this one hasn't got, the iTet Maple hasn't got any FTDI chip. It's a bit more inexpensive. Also, it's a bit more inexpensive compared to the usual Maple because this is actually a clone. Then there's also a big difference on the silk screening, because the chipKIT has got better and more detailed silk screening than the iTet Maple. You can see here we only got the pin numbering, and on this we got even more. We got, of course, the pin numbering, but we also got this. This is PWM digital, this is analog, and the different pins of all of the things. Over here we also got what types of power we have, and this isn't actually listed on this connector. There isn't even numbers for that. So in that matter, the chipKIT board is a bit better. But now let's see how well they performs compared to each other. One of the tests I will be doing is a speed comparison of output GPIO, output toggling, and this can be done in different ways. But I'll show you how this testing can be done, and the code can also be found on our blog, so you can do the test yourself if you would like to compare the board to something else. Here we got the two boards, and over here we got my oscilloscope. This is the Rigel one, which you can also view a review of by clicking the link down here. I'll use that for the testing of the output toggling frequency. So I'll simply connect these two probes to each board so we can make a comparison. Back at the computer, I've now opened both the IDEs, the one for the chipKIT, the MP IDE, and the one for the iTet Maple, the Maple IDE. And I've made some speed test code, which you can see here, which simply initializes the pin 2 as an output, which I'll be using, which is the one connected to the oscilloscope. And then in the loop, I'll be doing some toggling of this output pin in different ways. The first way will be by simply toggling the output by using the digital write, as you can see on both of the in both cases, while where the digital write is then internally in the compiler converted to the appropriate register command writes, where I then in the second case will simply use these register writes directly, which will indeed speed up the toggling frequency because of the digital write taking much longer. Another case will also be the loop, that the loop will take some time in itself. When reaching the bottom, it should go back to the top and then restart at the same position, and this takes some time. And the chipKIT is running at 80 MHz, and while the iTet Maple is only running at 72, but there might be a difference anyways. So we'll make this comparison and see how it performs. So now I've plugged the two devices into the computer. So let's load up first the chipKIT. And program that. Sorry, I should remember to uncomment these lines, because we'll test the digital write first. So I'll have to program once again. So we program the chipKIT first, and on the oscilloscope I'll set it to run and set it to the chipKIT. So the chipKIT is the yellow one, and the blue one is the iTet Maple. So now the chipKIT has been programmed, and we will program the iTet Maple too. And in the meanwhile, let's have a look at the oscilloscope signal and what it shows to us. Well, so we will have to wait. Right, this is the chipKIT. The output from the chipKIT pin 2 goes to the oscilloscope, the yellow one, where we'll goes to the oscilloscope, the yellow one, where we'll see this square wave with a frequency of 653 kilohertz. So by using the digital write in the loop, we'll get a frequency, toggling frequency of 653 kilohertz. But you might notice this frequency is actually walking and changing a bit, so it's not that static. But which is very noticeable is that the duty cycle is very similar, so it's look like it's 50 and 50%. The cause of the frequency changing might be due to the loop taking difference in time. But let's have a look at the Untitled model and see what happens with that. Well, at the computer, I can see that the device hasn't been programmed yet, so we'll select the right COM port and try uploading the code again. And now that has been programmed, let's look at the oscilloscope. You will see a much more stable frequency. It's not varying that much as compared to the chipKIT. And you'll also notice that the frequency is actually a bit higher. Now it's 710 kilohertz. But it's still not much compared to the frequency of the crystal running at the internal oscillator running at 72 megahertz. So instead, let's go back to the computer and load the next two lines, which is doing a direct writing to the registers of the port registers. On the PIC, we have the so-called LAT registers, which are used for setting or resetting output bits. And in the first line, I OR the 8-bit because of pin 2 on the Arduino is being pin 8 in the port D of the PIC 32. So I'm ORing the bit 8 to the port D register, which will turn the output on. And then in the next line, I'm clearing that bit by ANDing everything else than bit 8. And I'm doing the same on the STM32 on the Mabel, where I simply write to the BSRR or the BRR registers for bit set or bit reset. And here I can this STM32 has got these registers for setting or resetting, so I don't have to do the same OR or ANDing. But the code is the same, so let's upload that and we'll do the same and see. Oh, now I started both at the same time. I shouldn't have done that, I think. Oh well, I think it worked. Now, back at the oscilloscope, let's have a look at the frequency on the chipKIT. Now this has become much faster. Now we have a frequency of 5.7 megahertz instead of the 653 kilohertz before. But yet again, you'll notice that the frequency is varying a bit, and that also you'll notice if we stop, you'll notice that the top time, the on time, is actually not as long as the off time. And this is due to the loop, as I said, which can take difference in time from the loop itself, so it takes longer when it reaches the bottom to go to the top than simply just toggling. If you go to the cursor mode, we can make a manual cursor and go to the position where the output pin is being toggled high, and then this is the time for it to toggle from high to low, which would be the same as toggling from low to high. So actually it should have been toggling to high at this position, but then we have some more low period because this low period will actually be placed here because of the loop has to go back to the start of the commands of the register writings. So let's switch to the ITET Mabel and see how well that performs. Remember the frequency on the the frequency on the chipKIT, 5.7 megahertz. Now on the ITET Mabel we actually have a much lower frequency, only 2.4 megahertz. So that's a bit less, and we will also notice that the frequency is the duty cycle of the frequency is very small. Indeed, we have small peaks, which is here now it toggles the output, sets it high, and then it sets it low just afterwards, and then we have a lot of time before it is set high again. So all this time is actually also the loop. So if we compare these two, the loop on the Maple is actually taking longer to go back and redo the loop than on the chipKIT. So that's not very good performance, and we will have to be aware of this time we're talking. If we go to measure, we can find out that this is actually I'll go here and change that to channel 2, and we'll find out that this, how long this actually is, because from here, whoops, from there to there, you've actually got 372 nanoseconds. So that's almost a half of a microsecond it takes for it to go from the bottom of the loop to the top. That's actually pretty long. So instead of that, back at the computer, we could instead well, use a toggling command, use the arithmetic of toggling. Here we just invert the bit, and the same could be done on the STM32, but this might not do any big difference. The duty cycle will be more precise because of us not having two commands that will be executed after each other, and then whoops, it has to wait for this to jump down to the next line, to the top of the loop. So instead of this, we could do another thing, which is writing all the registers commands in a series. So what I've done is that I've wrote 30 times of this, equal to 60 lines of code, 30 times of toggling the output pin in series, so it will toggle the output 30 times with the right frequency, the frequency of the time taking of writing to a register. It will do this 30 times before having to wait for it to go back to the beginning of the loop. So this will make a higher frequency, as it doesn't have to wait as many times for the loop to go back per toggling, to say. So let's upload that to the chipKIT and to the ITET Mabel afterwards. Done uploading, and on the ITET Mabel, also done uploading. Now let's have a look at the oscilloscope when the chipKIT has been initialized. Yet again we'll see some varying frequency. It seems like the loop on the chipKIT is very unstable. It's not the same time from loop to loop. But we'll notice the big increase in the frequency from the frequency of before 5.7 megahertz to now 7.63 megahertz is a big increase. And if we stop it, we'll also notice that the duty cycle has been much more static. It's even. So we have almost 5% off time and 50% off time and 50% on time. And if we scroll through we then see some spaces, which is where it goes back to, it jumps back. This is the time from it jumping from the end of the loop to the start of the loop. And then we got some 30 toggles again. And that is also why this measurement will be higher, because it the waiting time is now less compared to the amount of toggling. Remember, this is a calculated value, but from the internal frequency counter. Okay, now let's have a look at the ITET Mabel. Start it again and change the triggering. Here we'll notice that the frequency on the ITET Mabel is a bit higher. So this would mean that the ITET Mabel is actually doing the register writes to the output registers a bit faster than on the chipKIT itself. But here we'll also notice that we got a big amount of flickering in the frequency because of the times of the loop ticks. Also here you'll notice some odd shapes that we got a large, small, and then we got a large space before we got some more. So this is not at all even compared to the chipKIT, but it's a faster frequency toggling. So that to be compared is that the ITET Mabel would be faster in some ways, and especially if you're doing the simple and the most common digital write command, the ITET Mabel, the Maple series, will be faster than the chipKIT. So that must be the conclusion of these tests, that the ITET Mabel is faster when doing digital writes, but the chipKIT will be faster when doing direct port writes. So you'll be able to get faster update rates actually with a display like this on the chipKIT than on the ITET Mabel, because of the library using direct port writes. Alright, that's a comparison of these two boards, and I think we should go back to some pro and cons of this board for the last part of this review. So for the test you've seen until now, I think you've also been convinced that this board has got indeed has got some more performance than the usual Arduino, Digilent or Uno, or also the Mega. This is definitely a great board with a lot of peripherals, but it has also got some cons. One of them is, in my opinion, that these jumper switches, these are a bit odd, that you can change and have to remember to change the switches to the right position when using, for example, a specific shield or library. Or also the SPI mode can be changed. I usually don't use SPI master or SPI slave mode. I haven't actually used it before, so I'm just using normal microprocessor being master and the device being a slave using the chip select. But another thing you have to take care of when using the board is the output maximum ratings of the IOs itself. These can give a maximum, you can draw a maximum of 18 milliamps per IO, but the ports itself are limited to a maximum of 200 milliamps per IO, and there is usually about 16 IO pins per port. So 16 by 20 will give 320 milliamps, so you can't actually use all of the 18 milliamps at all of the ports at the same time. Also, compared to the libraries that are already been ported to the Arduino, the MPIDE, it is actually great. There are some great references, and some of the most common libraries has been ported, though the wire library hasn't been ported yet. So if you're using some devices that will be using the wire, you are missing that and would have to wait for that hardware specific library to come out. Well, except for the USB functionality, as I mentioned, missing, there's nothing else I can come up with that is missing on this board. This board has got the required peripherals and power to be a good a good performance board, but in the Arduino form factor and capable of being programmed in the Arduino language. The I2C though is also a bit limited on the board. There is no pull-up resistors on the board itself, so if you are connecting I2C devices to the board, you would have to remember to put the required pull-up resistors externally, because remember that I2C is requiring pull-up resistors for its two wires. But I think that's mostly it for this board. I would say that if you've got interest in another Arduino form factor board but requires the extra speed, as I've also said with the iTed Maple, you should definitely have a look at the chipKIT. In our comparison, the chipKIT has also got some more power when it comes to writing to port registers, and it's got 80 MHz, so you got a decent amount of power in this. And 128 kilobytes isn't a lot, but compared to it being a 32-bit processor, but I'll say that it's enough for most of your applications, especially because of the IOs. So definitely a great board you should have a look at, and also if you've got time and the money, you should have a look at the Max 32, the bigger brother I told you about. And with that you will of course get the extra Ethernet USB functionality and a lot of extra IOs. So I hope you enjoyed watching this review of the chipKIT Uno32 I've got from Fonil. So thank you very much for watching, and please rate, comment and subscribe, and remember to visit our blog for more information, the code and the I/O diagram. Thank you for watching.